here we are doing a problem with a box, and there is a drag force, just like we did before. So this v, by the way, is not the force. That's just the direction of the speed of the object. So we want to begin with the free body diagram in part A of this little dude. So we've got an applied force. We have this kV going backwards force, the drag force. We have a normal force pointing up, and we have the weight of the object pointing down. Make sure you label all of those forces. Now it says write, but do not solve a differential equation, so let's go ahead and do that. What they really want is Newton's second law. So we have the applied force minus kV, and that equals ma. And to convert this into the differential equation we want to solve, we're going to have Fa minus kV equals m dv dt. Just in case they want us to go a step further, I'm going to isolate the dv dt, but this should be fine. Now it says find the terminal velocity. So for part C, we're going to set A equal to 0. That's when you get A equals 0 when forces balance. And that leads to terminal velocity happening. So I'm going to have Fa minus kVt equals 0. And so my terminal velocity is going to be F applied over K. Now, finally, we are going to be able to, you know what? I'm going to skip to part E, actually. And the reason is I want to show you something. So we have the velocity as a function of time. And I just want to remind you that the velocity in these, when we start off at a speed of 0, so when we start from rest, as it says in the problem, we start at a speed of 0, and we're going to actually approach an asymptote, and that asymptote is going to be v terminal, which we just solved for as F sub A applied force divided by K. So you can actually skip straight to part E, and then you're going to get about 10 out of 15 on this free response, or 9 out of 15. Now let's go ahead and actually get this differential equation as a function of time and solve it for the velocity as a function of time. So I've got it right here. I'm just going to move it. And now let's do our calculus exactly as we did before. I'm going to do this a little bit more rapidly because you've seen this a couple times. So I'm going to have Fa minus kV times dt equals mdv. Let's do a little rearrangement. So I'm going to have dt over m equals Fa minus kV. Now I'm going to do a little u substitution. So I'm going to say u equals Fa minus kV, and du is going to equal negative k dv. So I can actually, you know what? And I forgot to add one thing here to my little integral side. I forgot to make this here the dv. I forgot to put the dv there. And what I'm going to do is I'm going to close the parentheses here. I'm going to add an integral sign to each side so that this u substitution looks a little bit more natural. And actually, sorry, I actually set this up wrong. Let me just back up here. So this is the differential equation that I want to solve. And I'm going to get velocity as a function of time. And I want to note that the initial velocity is 0. So I'm going to go a little bit quicker than you're used to me going, because I've done this a couple of times for you, and we've done it a couple of times in class. So we're going to get dt over m equals dv over Fa minus kV. Now let's do a u substitution. So we're going to have u equals Fa minus kV, and du equals negative k dv. I can now make that substitution. You know what? And let me just put some integral signs in there so this looks a little bit more like calculus class. So let's put our substituted orange stuff into the equation. So I'm going to have here negative du over k, you'll need to sit with that algebra and figure it out if you haven't already, times 1 over u with an integral sign equals the integral of dt over m. So this is going to give me t over m on this side, and I'm going to actually get on this right side negative 1 over k times the natural log of u plus c, if you want. I can put it here. Maybe I put it on the other side, doesn't matter. Now, I'm going to rearrange negative kt over m equals ln u plus c. There's no point in multiplying the c times the k over m. It'll just be a new constant. So if this weirds you out that I have the same c here and here, ask JLu. So now let's go ahead and solve for this integration constant c, and we get that from the initial conditions. So I'm going to have negative k times 0 over m equals natural log of, let's swap out the u for what it is, that's going to be fa, okay, minus 0. So what I'm getting here is that plus c. So my integration constant is negative natural log of fa. That's awesome. Now let's go back and see what our expression looks like. So we have negative kt over m equals natural log of, and let's just swap out the u, fa minus kv minus natural log of fa. I'm going to rewrite that as a fraction, so I'm going to have negative kt over m equals the natural log of fa minus kv over fa. Let's exponentiate both sides. So we'll have e to the negative kt over m equals fa minus kv over fa. Now I'm going to multiply both sides by fa, so I'm going to get fa e to the negative kt over m equals fa minus kv. When I isolate v, I'm going to end up getting v equals fa divided by k times 1 minus e to the negative kt over m. And that is our solution. I have left out steps. I want you to fill in that algebra. That is a really important thing that I want to challenge you to do. And I want to also challenge you to be able to solve this problem fairly rapidly, because this is something that is going to be on the AP exam, if not this year, the next year, and definitely in your engineering physics classes. So that's a little guide on how to do the 2013 problem.